Okay, on the previous part, 6.2 part 1, we talked about the definition of orthogonal vectors, and orthogonal vectors is, orthogonal means perpendicular. You can prove that two vectors are perpendiculars if their dot product is equal to 0. And the other thing too is if their dot product equals 0, how do you tell, and that makes them perpendicular, how do you tell something if the two vectors are parallel? Well, they're parallel if this right here. I'm trying to think what's the best way to verbalize this. They're parallel if and only if u equals k times v, where k is a scalar multiple. So what really that means is that they're parallel if you're just multiplying one of the vectors by a number, and so it makes it 3 times smaller, 3 times bigger, just some kind of one vector is a multiple of the other one. So how we're going to do this one, I've already done example 4 on part 2, or in part 6.2 part 1, but I'll do it again just in case you need to be reminded, because at this point sometimes we do need to get reminded. So I want to prove that these two vectors are perpendicular and that their dot product is equal to 0. So how you prove that their dot product is equal to 0, I'm going to multiply 2 times negative 6, that's your A component, your A components I should say, and you're going to add it to the B components, the product of the B components. Well, 2 times negative 6 is negative 12, plus 3 times 4 is 12, so their product is 0. Therefore, these two vectors are perpendicular, or orthogonal. It's a lot easier to write perpendicular on with this, but or orthogonal. Okay, now for example 5, ABC, they ask if can we prove that these vectors are perpendicular or parallel or neither. So looking at example A, 5A, you have u is the component form is 2, negative 7, and the component form of vector v is negative 4, 14. Now look at these two, and you kind of can see that you have the A component of this one and the A component of V are kind of similar. So what would I multiply U by to get V? I'm thinking there's some kind of scalar of each other. One of the ways is that 2 times what number is going to equal negative 4. You do it that way, and when you do that, your k value, or you realize that your k value is negative 2. So just FYI, let's talk about how to multiply scalar again to a vector. So if I have negative 2 and I'm multiplying it times the vector form of u, negative 2 times 2 is negative 4, and then negative 2 times negative 7 is positive 14, and lo and behold, that's equal to vector v. So we proved that these two vectors are parallel, therefore parallel, because they're scalar form. And your k value, your scalar is just a number, it's a constant, is negative 2. And again, scalar, it's kind of like you're amplifying your vector. You're making it longer or skinnier, or not skinnier, it can't be skinnier, but longer, or you're changing the direction. It's just a multiple of the other one. So now looking at example B, it's asking us if u in its component form is 2, 5, and v in its component form at 10 thirds over 4 thirds. Well, I'm not seeing any pattern, but then again, let's see if there's another way of doing it. So hold on just a second. If there's a good way of doing that one, but let's see. 2 times what we did over on A was we 2 times what number? I guess I probably should have called this x, but 2 times what number would equal 10/3? Well, if I multiplied for x instead of, I really should have done that in a, but whatever. This would have been 5 cross multiplied or divide to be 10/6, which reduces to 5/3. Now let's multiply that number times my b component. 5 times 5/3, that's going to be 15/3, which does not equal the b component of vector v. So they're definitely not parallel. So let's see if they're perpendicular. So let's multiply their dot products and see if they're going to be perpendicular. I am running out of room, so hopefully you've gotten that. I'm going to erase it. So let's erase that one. So they're not. I'm going to erase this one too. So let's see if I multiply the dot product and see if they're perpendicular. 2 times 10/3 plus 5 times 4/3. This is going to be 20/3 plus 20/3. They have common denominators, add them numerators. Well, lo and behold, guys, that's not 0. So B is neither parallel or perpendicular, so it's neither. So the answer for B is neither. Okay, let's see what answer for C is. Again, let's see if I know I can't. I want to see if I do the dot product first. That's typically what I do. It was very obvious in A that there was a scalar form, so let's do the dot product of C first and see if that doesn't get me something. -3 times 20. I'm going to add that to 4 times 15. Well, -3 times 20 is -60. 4 times 15 is 6. Oh, saying it, but I'm writing something else. 4 times 15, I'm hoping, should be 60. So their dot product is 0. Therefore, these two vectors are perpendicular. Okie dokie. Now, let's do... Alright guys, here we go. We are going to do this last problem. It is asking us to find the interior angles of a triangle with given vertices. If we... The vertices being -4, 5, 1, 10, and 3, 1. I'm going to draw this on Cartesian plane, and I have just going to approximate 1, 2, 3, 4. Let's see. This is A. B is going to be right about here at 1 and 10, and C is going to be here about 3, 1. So A, B, C. Alright, so I'm going to call this point A, point B, and point C. Okay, what's weird about this is that it wants the angles in between these vertices. So it really wants angle A, angle B, and angle C. The most, I guess the best way of doing this is if I'm going to do a vector AB, and then I'm going to do the vector AC, and I'm going to find the angle A. And then to do that, the reason I'm doing that is I have vector AB, and to find that I need to put it in component form. If I'm starting at A and ending at B, I need to subtract 1 minus a -4, and then 10 minus 5, and write AB in component form, which would be 5, 5. I need to do the same thing with vector AC. In vector AC, I'm starting at A and ending at C, so I want to have 3 minus a -4, and then 1 minus 5. And guys, I've done this problem several times today. The problem with this is that because you want to find the angle in between these, start at A and go to B, and start at A and go to C, and then that way you can find the angle in between. Otherwise, it just doesn't work. I've done it several different ways. So I've found my vector AB and AC. Now I want to find the magnitude of AB. Since AB is already in component form, I can do it the square root of A squared plus B squared. It's going to be the square root of 50. And the magnitude of AC is going to be 7 squared, or square root of 7 squared plus negative 4 squared. And that is the square root of 65. Okay. On the previous section 6.2.1, part 1, yeah, 6.2, or I don't know if it was 6.2, I think it was section 6.1, we learned how to find the angle in between the two vectors. Actually, I think it's this, I don't know which section it is, but we use that equation of the cosine of theta is when you multiply the two vectors times each other over the absolute value of each vector. So I can find, I'm going to use this equation, but I already have my, so I'm going to find cosine of A. To do that, I need to multiply AB, vector AB, times vector AC, all over the absolute value of AB, times absolute value of AC. Okay? So cosine A, I need to do that, in order to do that I need to multiply AB, here, let me erase this, in this equation I need to multiply vector A, B, and AC. That's your dot product, and that's kind of what we were doing before. Let's see, AB times AC. I'm going to take 5 times 7 plus 5 times negative 4, and that's going to be 35 minus 20 equals 15. Okay. Okay. So, multiplying AB times AC is going to be 35 minus 20, which is 15. Alrighty, so now what I'm going to do is plug all those values in to this equation and find angle A. So cosine of A is A times B, which is 15, divided by the absolute value of AB, which is the square root of 50, times the square root of 65. Okay, but if I want to find angle A, I got to do the inverse cosine of this. So angle A will be the inverse cosine of 15 divided by the square root of 50 times the square root of 65. Which angle A is going to be 74.74 degrees. Okay, so on the previous problem, here we go again. Not previous problem. The previous slide we found, I was trying to find the angles between all these vertices, and I called point A was 4.45, B was 110, and C was 3.1. Okay, so I found on the previous slide angle A was 74.74 degrees. Okay. Alright, now the thing is, what I had to remember, I had this triangle, A, B, and C. I've already found angle A. Found this angle. Now I need to do the same thing. I want to find angle C. But to do that, I need to find vector CA and CB. I'm starting at C and ending at A. So I need to take my A components and subtract them from my C components. So I have negative 4, sorry. Negative 4 minus Okay, just so you're not getting confused, because just a second ago I was getting confused. I'm starting at C and I'm going to A. So I gotta take my A components and subtract C from them, because this is now A is my x2, like where I'm stopping. So negative 4 minus 3, and then 5 minus 1. So we'll see A in component form is negative 7, 4. Right? I did the same thing with CB. I'm starting at C, aiming at B. So I'm going to take 1, minus 3, because I'm ending at B, and then 10 minus 1 would be negative 2. Negative 2, 9. Alright, again, I keep getting, I have to go back and remind myself that, if I'm with CA, and why that's a little different than the previous one, because I'm starting at C, that's why, because C is first. I'm starting at C and ending up at A. So C, my C components are going to be my x1, y1, and my A components are going to be x2, y2. So I got to take my negative 4 and subtract them. Let's do this. Negative 4, that's my x2, minus my x1. Same thing with my 5 is y2 minus y1. And the same thing with CB. I'm starting at C and ending at B. So I got to take, when I do the CA, my A are going to be my y2 and y1. And then when I do CB, this is going to be my x2 and y2. So I take 1 minus 3 and 10 minus 1 when I figure out CB. Alright, easily enough to get confused with. Let's keep going. So now what I need to do is in my previous problem, like on the previous slide, I needed to multiply or find the dot product of these two vectors. Might as well do that now. So it's going to be negative 7 times negative 2 plus 4 times 9. So that's going to be 14 plus 36 to 50. Alright, and then I need to find the magnitude of CA. Magnitude of CA is going to be the square root of negative 7 squared plus 4 squared. Get my little squares in there. Do that a little bit better. Hold on. Square root of 49 plus 16, which is the square root of 65. And then I need to find the magnitude of CB. It's the square root of 2 squared plus 9 squared. Square root of 4 plus 81, which is the square root of 85. Alright, now I gotta plug this into these little equations this time. I find an angle C. There's going to be inverse cosine of 50, because that should multiply your two vectors times each other over magnitude of CA times magnitude. What am I doing? Sorry. 60 square root of 65 times square root of 85. Put this in your calculator, and you're going to have angle C, which is 47.73 degrees. Alright, so now I have angle C, angle A. Okay, now if I want to find angle B, it would be 180 minus angle C minus angle A. Angle A is 75 So angle B is going to be 57 by 3 degrees. Okay, now I did all that. Now try problem. I know you'll have a problem like this in your homework. This is like problem, I think, 30. Number 30 on page 520. I think that's the right page. Yeah. Okay. Good luck. I hope all is well.